Hello and welcome to a cover lesson on energy transfer. Your date will be going here, just as normal in your books. Your title, cover lesson, energy transfer. Your keywords are dual, efficient, transferred. Pause this video at any time. I'll be zooming in and out as we go. So your do know activity, your questions are there. You don't need to write the question, just the answers. So the first question is, what is the charge on an electron? Question 2, what is the boiling point of water? Question 3, name a good conductor of electricity. 4, what is the chemical formula for water? 5, what process do plants use to convert sunlight into sugar? And your challenge question there, give the units for the following quantities. And they are speed, distance, time, temperature, energy, and power. I'm going to give you the answers in just a sec. Okay, so the answers to the do know activity. What is the charge on an electron? It is negative. Boiling point of water is 100 degrees Celsius. Any metal really is a good conductor of electricity, but if you've put copper, even better. So copper is the best conductor. What is the chemical formula for water? It's H2O. Process that plants use to convert sunlight into sugar is called photosynthesis. And then here are your units. So meters per second is speed. If you put miles per hour, maybe accept it, but we'd prefer meters per second because your standard unit for distance is meters and time is seconds. Temperature, degrees Celsius. Energy, joules. Power, watts. So as always, we're going to get some information in our books and then we're going to do some examples and then you're going to do some practice. But the first thing I need you to get into your book is this little blurb here, which says energy cannot be created or destroyed. It can only be transferred. What does this mean? It means that all the energy in the universe is finite, really. It's already made. There's no more energy that can be made. It can only be transferred now. You can't destroy energy either. It just gets converted into other things. And I'm going to give you those eight things now as we move down. So it's very important. Energy cannot be created or destroyed. It can only be transferred. So there's a fixed amount of energy within the universe. And we are just, I shouldn't say we, but this energy is just getting converted back and forth, different types of energy. We can scroll down now. So I've got the 8 types of energy. Now these are not obviously the 8 types of energy, but it's a way to remember. We call this a mnemonic. Okay, so the English stands for, I wonder if you could guess it. The first one is electrical energy, okay? Electrical. We should all be familiar with electrical energy. It's a big part of our lives. We use it everywhere. K. You might be familiar with this word. Kinetic. Kinetic. What does it mean? It's a movement. So any type of movement, the movement that you're using to write this word is a kinetic energy. So any type of movement energy. Car moving, ball dropping. Hate. So English kids hate heat. Heat. We also call this thermal, but exams and examiners will accept either really. So the heat that you're generating from this morning's breakfast. So you got this morning's breakfast, which is some sort of energy being converted into heat to keep you at a stable 37 degrees Celsius. Learning stands for light. A very, very handy energy that helps us to see. And plants photosynthesize. And without plant sugar, none of us would be here. Don't know if you've guessed G now. If you drop your pen, gravitational. So gravitational potential. It's a potential energy. So if you're holding your pen, the only reason it's staying in your hand is because you've got friction on your hand and it's holding that pen. But if you were to let go of that pen would fall. to the nearest object. And if that object's removed, that pen's going to keep falling. C, you might not get this one. This was a tough one. Chemical. This is probably the one that everyone forgets about, but it's a big one. Chemical. Chemical energy. The food that you ate this morning, your breakfast, was stored chemical energy. The same as petrol is chemical. Batteries that you use in your mobile phone is a chemical energy. S, sound. The sound of my voice. The sound of an explosion. The sound of water falling. It's all sound energy. And then the last one, again, you might not get this. It is called elastic potential. Elastic potential. Think of a slingshot or a spring. So potential, this held elastic by elastic potential energy there. So that's the 8 types of energy. They need to be down in your books, along with the energy that cannot be created or destroyed. It can only be transferred. So it's nice to have these 8 types of energy, because they're going to be going from one to the other and vice versa, okay? Remember I said now, there's just a fixed amount of energy in the universe, on Earth, okay? And it just gets converted to back and forth these things. And I'm going to show you how that happens. So then, in your book, under the nice title of Energy Transfer Examples, I'm going to give you 3 examples, and then you're going to have a practice on some. So we've got a nice little hairdryer there, okay? Mr. Gordon would be very, very proud of my diagram. This is obviously a hairdryer. Now we need to talk about the energy in and the energy out. Remember, energy in gets transferred to something else. You can't waste that energy. You can't create this energy. It just gets converted. So what's the first thing that goes in? And I'm going to change my color pen here. I'm going to stay the same. So energy in is going to give us energy out. What do we need to do to this hairdryer to get it to work? We need to plug it in. Where do we plug it? Into the mains electricity. So the energy that needs to go in is electrical. Okay? The hairdryer needs to be provided with electrical energy. And that's all really. That's all that goes in. What comes out of that hairdryer? Well, I'm thinking 3 things. You might think of more, but I think the main things that we're going to get from the hairdryer is heat, or you can call it thermal. I'm going to stick with heat. I'm going to underline heat. I'll tell you why in a minute now. Plus, what else do I get? I get the movement of the fan to blow it. Okay, pointless having heat just there. I need to blow that heat out. So I'm going to get kinetic, which is movement. Kinetic. I'm going to also underline kinetic. Plus, get something I don't really want here. Okay, the sound does nothing to dry my hair. We can call this a wasted energy. Okay, and we can call these 2 useful energies, which is why I've underlined them. So I've underlined the energy that is useful to this device. So I'm going to plug it in. I'm going to suck some electricity out. I'm going to turn that electrical energy into heat. Okay, there's a filament in here, and it's going to turn the fan. It's going to blow the heat. Unfortunately, though, we're going to get the sound of that energy being sort of pushed, which is the motor, and we're going to get some sound. I don't really need this sound, so it's a wasted energy. So this is useful energy, heat. Kinetic is useful, sound, absolutely pointless, but I gotta have it. Okay, you can get more efficient hairdryers, and that word efficient there we'll come on to in a bit. They're not so noisy, but generally a hairdryer is quite noisy, and it's just unfortunate. So that's all we've got to do really there, okay? Well, we're on the first step. We're going to do the television now. Again, my drawing is amazing. And we've got energy in and energy out again. So if you need to pause the video just to get this example down, please do. But I'm going to carry on now. What do we need to do to get this television to work? Again, we're going to plug it into Electrical. We're going to plug it into the mains. Do I need any other energies going in? No, the plug will do it, okay? What is this going to get converted to? Many things, really. It's going to get converted to, well, I need to see what's going on. How do I know that, how do we see that television? Well, it's got light pixels. It's got pixels in it, little LEDs, so that's light. I'm going to underline that because it's very useful. Pointless having a TV without it. Sometimes I just like to listen to the TV, so that's going to be sound. In this case, sound is a useful energy. It's really useful. Okay, if I'm watching the news, I need to hear what they're saying, plus, I need to see what's happening. So light and sound. Now, TVs these days are very, very efficient, and you don't get a lot of this, but we are going to get some heat, some thermal, which we don't really want. Okay, it's not of any use to us. And I think that's pretty much it. You could say a little bit of kinetic because of the speakers. The way a speaker works is to vibrate, and then it pushes that sort of wavelength out. But for now, we're just going to keep things simple. We've got light, we've got sound, useful energies, and your heat, because your TV will warm up, especially if it's left on all day, is a wasted energy. We don't really need it. Okay, last example then, a car. Now, you could go bonkers on a car because, there's a lot of energy transfers here, but we're just going to try and keep it as simple as we can. Let's think of a motor, maybe rather than a car. Okay, so what goes in? Not electricity this time, unless you've got an electrical car, but even then it probably requires some sort of other fuel. And fuel is chemical, a chemical energy. That's stored chemical energy. And that's going to give us, so if you've got a hybrid car, maybe you've got two energies going in here. Maybe you've got chemical plus electricity. But my car's just diesel, so it's just chemical energy going in. What's my useful energies now? What am I getting out? Well, I really want my car to get me from A to B. So I'm going to have kinetic, which is movement. I'm going to underline that because it's a useful energy. Plus, maybe it's dark and I want to see, so I need to turn my lights on. So light energy is a useful one. I need to see what speed I'm doing on the dashboard. And here is where it gets a little bit tricky because sound, yeah, I could have the radio on and that's a useful energy. But more often than not, we try and, well, I say we, I don't. They try and make cars quieter to lose less energy as sound. So I'm going to put sound down. I'm going to put sound. Now, sound could be a useful energy because you need the radio, you need the horn to tell people to get out of the way. Here I come. But more often than not, the sound is wasted as the engine ticking over. It's a motor. And the sound is coming from that motor, which is wasted. It's a useless energy. But cars these days are really, really quiet. So kinetic plus light plus sound. I'm going to leave sound as a wasted. And then you've probably guessed it, this last one I'm going to say is plus, oops, I don't know what is happening there, plus heat. Okay, your car is going to get warm. And again, it's no use to us in the grand scheme of things because, again, it could be argued if it's winter and you want to warm yourself up, you put the heater on. So this is why a car is a tricky one. But I'm going to leave it like that. And there's probably loads of others you can think of. Okay? But we're just going to leave it at that. So I'm going to give you some practice on this now on the next one. So your three questions to practice. I've got a battery radio, and I've specified it's a battery radio, something you can take around with you, mobile phone, and a waterfall as a challenge. See how you do with these. Okay, so this is what I've got. So I've got a battery radio, energy in, energy out, as always. I've got chemical, because your battery is a chemical, stored energy. That goes to sound, which is a useful energy, because I want to hear the music. Kinetic, I've put as a useful here, because of those speakers. Remember I said about the speakers being, they have to vibrate. Okay, so that kinetic energy plus thermal is wasted energy there. Didn't want that. Your mobile phone, chemical again. You need to, even though you plug it into the electricity, okay, to charge the battery, essentially it's the battery is what's giving you the light, the sound, the kinetic, if your phone's going off it buzzes, plus your thermal. Okay, your phone's going to warm up. And then this last one, the waterfall, the challenge, because gravitational makes the waterfall. So gravity makes the waterfall. It turns into kinetic energy, which I guess could be a useful energy. Plus your sound is going to make a noise, and it gets warm. Okay, that movement energy, especially at the bottom where the water hits more water, that friction is going to cause heat. This could be used to generate electricity. So electricity then could be your useful energy. And when you come on to sources of energy, how we get our energy, hydroelectric is a big one in this case. So that's why I've just thrown that in. Okay, we're going to move on now to actually calculating the efficiency of some devices. Okay, so this is your efficiency equation. I'd like you to get this down in your book. So efficiency can be calculated by putting your useful energy over your total energy and then times it by 100. So you're going to divide your useful by your total. So the small number is always going to go on top. Your big number is always on the bottom because it's a percentage. And you're going to times that by 100 to get it into a percentage. Let me give you an example. The hairdryer, back what we was the first one we did. So let's just say now the electrical energy in a hairdryer was 500 joules because energy is measured in joules. And let's just say 200 joules were the heat and the movement, the kinetic, and then the 300 joules was sound. So I've got a wasted energy of 300 and I've got a useful energy of 200. How do I calculate the efficiency of this hairdryer? Well, I'm going to use this equation. Efficiency equals useful over total times 100. And this is how I generally write this. I go percentage equals, so my percentage there, efficiency, equals useful over total times 100. And then I would actually replace these values. So what's my useful energy here? Is 200. So this is 200 over, what's my total energy? My total energy going in is 500. 500 times 100. Now when you do this on a calculator, I would put 200 divided by 500 and then press equals. You're going to get a number and then times it by 100. Okay, because if you start typing it all in, it can get a little bit muddy. This is going to come out to be 40% efficient, I think. And let me just check that. Yes, 40% efficient. Let's go on to the next one. So my second example now, I have left something out on purpose because more often than not, they want you to calculate something. So your TV, I've got 2000 joules here. That could easily be represented as 2 kilojoules because there's 1000 joules in a kilojoule. The same as there's 1000 meters in a kilometer. But I've left it as joules. So there's 2000 joules going in, which from what I remember now for a TV was electrical. Then I've got 500 joules as, let's just say, light. Then I've got 800 joules as sound. Now these two are useful because I've underlined them. But there was a wasted energy, wasn't there? There was heat. Now, how do I find out how much wasted energy there is? Well, if I've got 200 going in, and I've got 500 being used on something, and 800 being used on something else. So 800 plus 500 is 1300. How much is being lost as heat? I would say 2000 minus my 500 plus 800. So I'm going to do that again. 2000 minus, well, 500 plus 800 we said was 1300. And now I'm going to get a value of 700. So 700 there is going to be what's missing here, 700. So we often need to calculate missing energies. Am I okay now? 500 plus 800 plus 700 should equal 2000. Remember, energy cannot be created or destroyed. It can only be transferred. Now I'm going to calculate the efficiency. So percentage equals useful over total times 100. Oops, that should be 100 there. So this is going to give us, what's my useful energy? Well, it's 500 plus my 800 this time. So I've got 1300 over, what's my total energy? My total energy is here, 2000 times 100. When I put this into the calculator, which I'm going to do right now, I've got 1300 divided by 2000. That's going to give me 0.65. Well, I know just from experience now, when I times that by 100, it's going to give me 65%. So I've got 65% efficient there. My third example now, let's have a look. Well, it's given me now this time my energy out, which is 300 plus my 200 plus my 200 plus my 100. We said there was four, didn't we? There was movement, there was light, and then we had sound and heat, I think, one of them. It doesn't matter which one's which. But I haven't got a total energy this time. So how do I calculate that? Well, you've probably guessed it. 300 plus 200 is 500. Plus another 200 is 700. Plus 100 is 800. So I must have 800 kilojoules this time. Now that is a lot, so I'm obviously making these numbers up. So 300 plus 200, 500, 700, 800, just checking that. So I've got all my, that's the first thing I would do. I would get them all figured out. And then I'm going to calculate the percentage efficiency here. So percentage equals useful over total times 100. What's my useful energy? I've got 300 because it's underlined, and I've got 200 there because it's underlined. So I've got a total useful energy of 500 over my total energy, which is 800 times 100. And that is going to give me, when I put it into the calculator, 500 divided by 800 is going to give me 63%. It's worth noting now, they are all in kilojoules, so I didn't need to convert at all. I just put my figures over one another. It's very rare that you will have to convert back and forth with these sort of problems. But sometimes, if this was like 800 kilojoules and then this was maybe, I don't know, just 800 joules, you would have to convert that to a kilojoule to keep it all the same. Anyway, let's have some practice now. That's not going to happen in the practice, so you just keep the numbers simple. This is what I'd like you to do. I would like you, under the title, subtitle of practice, draw this table. You've got 4 lines coming down. 3 lines coming down to give you 4 columns. And then in the first column, you've got energy in, which is going to be in joules, and useful energy, which is going to be in joules, wasted energy, joules, efficiency, which is a percent. I've given you some numbers, and I would obviously, on the first one, you're just working out percentage, efficiency, but you have to kind of work out the wasted energy here, you have to work out the useful energy here, you have to work out the total energy here, and this one, it's your challenge question, it needs the energy in and your wasted energy. Good luck, press pause, and I'll be back with the answers. So I've got the answers here, so just run you through it quickly. 3,000 useful, 4,000 total. It was 3,000 over 4, or 3 over 4, which is 75% efficient. I had a wasted energy here, but I could have done that without the wasted energy because it was just 280 divided by 370 is going to give me 76, and then I worked out the wasted energy because I subtracted 280 from 370. So 370 minus 280 is going to give me 90. But like I said, I didn't need it to work this bit out. Now I need this to work out the efficiency because it's useful over total. So I got 2,500 minus my 1,300, which give me 1,200. Now I can use this 1,200 divided by 2,500, and when I times it by 100, it's going to give me 48%. This one then, 80 plus 150, is going to add up to be 230 total. 80 divided by 230 is going to give me 35%. And then this last one, a little bit of thinking here. Well, if it's 25% efficient, that means that it's sort of a quarter efficient. So what's this a quarter of? Well, if it's a quarter, then you would times this by 4 to get your total, wouldn't you? So 150 plus another 150 is going to be 300. That would give you half then. That would give you 50%. And then to get it to 100% is going to be 600. You times it by 2 again. So 150, if it's 25%, goes to 600. So 600 minus 150 then is 450. Well done if you were able to get that, because that was quite tough. Okay, your what went well, and even better if today I am able to identify energy transfer and calculate efficiency. Even better if the next time you see this topic, which will probably be in Key Stage 4, and then we're going to use these things called Sankey diagrams to represent energy transfer. Well done, guys, and I'll see you soon.